This is problem 1446. It's on page 732. A 32.2 pound winch A has a radius of 1 foot and a radius of gyration of 0.8 foot. A cable wrapped around the winch passes over a massless frictionless pulley B and is connected to a 50-pound block C on a frictionless slope. If a 50 foot-pound couple M is applied to the winch A, determine the acceleration of block C and the tension in the cable. Let me transfer the figure to the board so you can see what we're looking at. So there's the winch mounted at A. And the moment applied to the winch is, again, 50 foot-pounds force. The cable that the winch is pulling on passes over a frictionless massless pulley. In other words, all this thing does is change the direction of the cable. It doesn't change the tension in the cable. And attaches to block C, which has a mass of 50 pounds mass. Now this mass rides on an inclined plane. I haven't shown them touching. I'm sorry, they should be touching. But there's no friction. The friction coefficient is 0 between the plane and the block. Now, one of the geometric things that they gave us, I think in the figure, maybe not in the text, is that this is just a 435 incline. They did tell us quite a bit about the winch or the pulley or whatever you want to call it. They said that its mass is 32.2 pounds mass. Really, they said it's 32.2 pounds force, but that indicates a mass of 32.2 pounds mass. They said that its radius of gyration is 0.8 feet and that its actual radius R is 1 foot. The radius of gyration just describes how the mass is arrayed about the center. Now let's go ahead from this and just calculate the moment of inertia. It would just be the mass of the pulley times the radius of gyration squared. So that's going to be 32.2 pounds mass multiplied by 0.8 feet quantity squared, which comes out to 20.608 pounds mass square foot. All right. Now, the kinematics are pretty easy. The kinematics, or the motion part of this, let's see. An acceleration up the incline of C is related to the angular acceleration of the pulley. So let's go ahead and let's draw a coordinate system like this. We'll take X, Y this way. That way Z is out of the board. And then let's see, so a positive Z angular acceleration of A relates to a positive X acceleration. That'll make the kinematics really easy. So AX, the acceleration of block C, is equal to R alpha. So we could also write that alpha is the acceleration of the block in the X direction divided by the radius of the pulley. Okay? So this talks about the block. This side is both talking about the pulley. And not that pulley, the winch. Okay, so let's start off with free body diagrams now that the motion study is out of the way. I guess there will be more than one, so let's make it plural. Here's the winch with a reaction in the Y direction and reaction in the X direction. An external moment applied M and tension applied from the cable. The block, on the other hand, on the incline, has only a normal force from the incline, because remember there's no friction, weight from gravity acting on it, and then tension in the cable. Now, let's be careful here and note that for the weight, for the weight force, the way the weight would break down if this was the weight side, well, it's going to be the 5 side, and then this is the 3 and this is the 4. If you're not sure about that, you might want to pause the video and think about that. But for relating to the weight, that triangle will help me out a little bit later. The kinetic diagrams, that's also plural, would be, let's see, there's the wheel, so I alpha is the only part I care about there. Obviously, it's not going to accelerate linearly. Similarly, the block is not going to accelerate angularly. All I'm interested in is its dynamic force up the incline. Okay, so now let's sum moments about point A, taking counterclockwise as positive. On the winch, we'll get m minus t times r. So I'm summing moments about the center. And that's equal to the kinetic moment, or the dynamic moment, I alpha. And if I sum forces in the x direction on the block, let's see, t is acting up the incline, the weight is acting down, but it's not all of the weight, right? It's this component, it's 3/5 of the weight. And that's equal to the mass times the acceleration of the block in the x direction. Now, from this equation, I can write that the tension equals MAX, the dynamic force, plus 3/5 of the weight. Now, if I plug this tension in to the moment equation, I'll get, let's see, the moment minus tension, but again, instead of tension, MAX plus W times 3/5 times R, to finish that off, equals I alpha. Okay? Now, I'm going to plug in one more thing. I don't want to use alpha. I want to use AX over R. So let me get rid of alpha. Let me make that substitution as well while we're at it. AX over R. And since I've been careful about my signs, everything should work out. So now let's see. I'm going to multiply through by R, so that I have M times R minus, let's see, let me go ahead and expand these out. We'll have MAXR. That came from here, but there's another R because I'm multiplying through by R, so R squared, minus W times 3/5 times R squared, same reason as before, equals IAX. And so then what I can do is get all the AX terms on one side. So let's have the moment times R minus weight, or 3/5 of the weight, R squared, equals IAX plus this term, mass times acceleration in the x direction, R squared. Yeah, I haven't made any mistakes so far, I don't believe. And so this is the same thing as I plus mr squared multiplied by AX. And so, solving for the acceleration block in the x direction, I get the moment times R minus 3/5 of the weight R squared divided by I plus mr squared. Now let's see, it looks like we've got, how did that happen? I feel like I can divide through by an R, but I think I should have been able to do that here. Let's see, make sure I did all this right. R squared, that's right. I feel like I've made a mistake. Oh yeah, I can't divide through by R because I doesn't have an R in it. Okay, good. Okay, this is going to be a bit messy, so let me get rid of the force equations and moment equation, or force equation and moment equation, and let's plug in the numbers. So AX equals, the moment is 50 foot-pounds force. The radius R is 1 foot. Minus 3/5 of the weight. What weight? Well, that must be the weight of block C. which is 50 pounds. Now look, the mass is 50 pounds mass, therefore the weight is 50 pounds force. We don't need the free body diagrams or the kinetic diagrams anymore. So where were we? We were at weight, and then R, the radius of the pulley, is 1 foot. That has to be squared. And then divided by I, well, we calculated I, that's 20.608 pounds mass, foot squared, plus the mass. What mass? Well, that must be the mass, excuse me. I haven't been careful here. That should be the mass of C, because that came from right here, which came from the force balance on the block. So I'm sorry, I should have had mass of C on that term all along to make it clear. So the mass of C is 50 pounds mass, just as that mass weighs 50 pounds force, and then times R squared, so times 1 foot squared. Check our units: pounds mass, foot squared, pounds mass, foot squared. That works. Pounds force, foot squared, pounds force, foot squared. So it looks like the square feet are going to cancel. Of course, 1 squared is just 1 anyway. So the feet are gone. And now I have units of acceleration of pounds force per pound mass. That is a valid unit of acceleration. But it's not the unit of acceleration we normally apply. Normally what we use is, let's see, 32.2 pounds mass, foot per second squared per pound force. So that way we get feet per second squared out of this whole mess. If you plug all this into your calculator, you'll find that the acceleration in the x direction is about 9.12 feet per second squared. And I don't even remember what they were asking for. Let's see, what did they ask for? Determine the acceleration of block C and the tension in the table, or in the cable. So the acceleration of block C, we've done that, that's right here. 9.12 feet per second squared. But what about the tension in the cable? Well, the tension in the cable we can calculate fairly easily. Let's see, because we have, or we had, an equation that said that the tension, I erased my equations too soon. Sorry, you might have to rewind the video to find this, but because of, let's see, what would be the easiest way? I guess the sum of the force equation would be easy enough. So it was MAX, where this was the mass of C, plus 3/5 of the weight was the tension. This was from summing forces on the block. So the mass of the block is 50 pounds mass. The acceleration is 9.12 feet per second squared. By the way, let me show you a trick. This acceleration without the conversion factor came out to about 0.283 pounds force per pound mass. If I were to apply that acceleration instead, notice I would get pounds mass immediately. So plus 3/5 of the weight, but the weight of the block was 50 pounds force. Plug all of this into your calculator, and you'll find that the tension in the cable is 44.16 pounds force. Now, if you were to calculate the tension in the cable with that block just sitting still, think intuitively, would you get more or less force? Well, you should realize that at static equilibrium, you get less force because some of this tension in the cable is going to accelerate the block.